All right, why do we have two of these?
That's probably the Google one still going.
Think it works? Okay, it's time. So here's your 2-minute warning. You'll see it.
Okay. All right, hello everyone. We have a jam-packed session for the next 95 minutes, so we're going to get started right away. This is the Vulkan, OpenGL, and OpenGL ES part of the Khronos BOF Blitz. My name's Piers Daniell. I'm going to be doing the OpenGL portion of it. And then after me is Tobias, who'll be doing OpenGL ES. Then after that, Tom will introduce Vulkan, and then we're going to have a bunch of speakers for Vulkan. And then at the very end, there's going to be a party, so I hope you all stay behind for that. That starts at 5:45. All right, without delay, let's get cracking. So, OpenGL update. You may notice that I'm not Bartold. He has been chair of the OpenGL group, which we used to call the OB group, for 10 years, from 2006 to 2016. And during his tenure, he produced 11 OpenGL releases. And this is a picture of him after his 11th release. He was quite happy to produce more, if that's what you want. But it was time for him to step down and move on to other things. So thanks, Bartold, for catching OpenGL up. It needed to be caught up during that time. So yeah, he did a great job. So I was voted in last year, and so this is me after my first release. But seriously, so I'm the new working group chair. I'm a principal software engineer at NVIDIA. I work in the OpenGL and Vulkan core driver team. I've been with the OB group since about 2008, and also in the Vulkan working group as well. But thankfully, even though there's a new chairperson, we still have veterans on the actual spec documentation stuff. So John Leach is still API specification editor, and John Kesenick is still HLSL specification editor. And taking over, my philosophy was that I want to just shepherd OpenGL through this transition with Vulkan now as kind of like the king of 3D APIs in Khronos. I want to keep OpenGL as a viable choice for people who need it. Serve the industry, serve our customers, serve you guys. So if you have needs, I want to make sure that the group serves those needs and represents the vendors in the group. Well, that is my mission. This SIGGRAPH is a big event for OpenGL. It is OpenGL's 25th birthday. In 1992, OpenGL 1.0 spec was released. I think it was in January 1992. So 25 years later, OpenGL is still going strong. There's not a lot of APIs that have been around for 25 years. Even Win32 API has not been around for 25 years. POSIX has, XLib I think has, but certainly hitting a quarter of a century for an API that still works. You can get the latest OpenGL drivers and it will still run OpenGL 1.0 software is quite remarkable. So those are all the releases that we've done since 1992, 19 in all. It's on its 25th birthday, we have another release, which I'll get to in a second. And to celebrate OpenGL's 25th birthday, we have some swag that you can buy for yourself. We have a Khronos store. There's a t-shirt you can buy, which I'm modeling right here. There's a tote bag, there's a mug, and who knows, some other stuff might appear. And if you stay behind for the party, you can pick up one of these commemorative drink cozies or beer cozies, but you can use it for water too. And it has the 25th anniversary printed on it. So OpenGL has changed a lot. Back in the day with the SGI reality engine, it could produce 1 million triangles per second, and that was running OpenGL 1.0. You can run that same app, that Ideas in Motion app, you can run it still today on the fastest card that NVIDIA produces, which is the Titan XP. That one can do 20 billion triangles per second. Of course, if you use the OpenGL 1.0 API, you'll never get 20 billion triangles a second. You have to use more modern calls, but it can certainly be capable of rendering that. And its performance is just crazy how much it's gone from 25 years ago to now. But still, the API still works. I just want to talk about one thing that's changed, that we've evolved in OpenGL, is the draw call. In 1.0, we had GL vertex, which you just put lots of them between your begin and the end, and you draw pretty things. GL vertex was 8 characters long. And we made it faster with draw elements at 14 characters. So that's like 50% faster, or over 50% faster. And then in OpenGL 1.2, draw range elements, faster still. But the king of all draw calls has got to be OpenGL 4.2's draw elements instance base vertex base instance at 45 characters long, which is almost 6 times faster than OpenGL 1.0. So we've regressed a little bit with OpenGL 4.6, but even though it's only 32 characters long, it's definitely the most powerful draw call there is ever. So I'm announcing OpenGL 4.6. There are many people who contributed specs and extensions that have gone into OpenGL 4.6. These are the companies and the individuals that have contributed. The design philosophy of 4.6, it was 3 years since 4.5, but we noticed that there was a bunch of extensions that all the vendors implemented. And it was important that we kind of compile them all together into a core specification, raise the baseline functionality for everybody, improve the conformance, and having a new version of GL is like a forcing function to make people actually pass conformance and it makes sure the quality of their drivers has increased. And of course, it remains 100% compatible with OpenGL 4.5 and all the OpenGLs before it, including OpenGL 1.0. And AMD, Intel, and NVIDIA, at least, maybe more, implement all the functionality that went into 4.6 in one form or another. Just packaging up is yet to come. So what's new in 4.6? The banner child, the big poster item for 4.6 is native spirv support. And I'll go into a little bit more detail about that. We've also added some stuff to improve rendering quality and performance, added some concepts from the approaching zero driver overhead movement that Khronos had a few years ago. The spec was released on Monday. You can download the specs. You can download the extensions and read those that went into the specs. NVIDIA has released beta drivers, which you can download right away. And if you look at the Mesa support matrix, most of the stuff is implemented already in one form or another. And I expect it won't be long until it's packaged up into a new version. So spirv. spirv has a rich ecosystem already. spirv is kind of like the native language that you can pass into Vulkan. And now it's a native language you can pass into OpenGL. And OpenCL, which it supported that already. spirv is an intermediate shading language. You can use higher level language for GLSL, of course, through the GLSlang tool to generate your spirv. And now the spirv can be passed directly into OpenGL. And you can generate the spirv with HLSL as well. That support is under development right now. And there's all these kind of tools and stuff you can use. So it's a rich ecosystem that now OpenGL supports natively. Now, the change that it will make is that before you used to create your program, create your shader, you add the shader source, and then you'll compile it. Now with spirv, that's changed. You actually pass in a shader binary, and then you specialize the shader. You tell it what all the specialized constants, what their values are, and your entry point. And that is how you create a program now. And another difference you'll notice with GLSL, especially the older original GLSL, one of the things you did is when you compiled your shader and built and linked your program, you would come in later and say, okay, where is this attribute? What location is that? Where is this uniform? What location is that? And then you program on your attributes and uniforms and other resources. But now with spirv, there's no reflection. All the bindings and everything are hard-coded into the shader themselves. And that's a better thing to do. It lends itself to better parallel compiling. So there's less stalls as the API asks the result of the compilation. You can do more things in parallel. So it's a good thing to do anyway to not have that reflection. GLSlang, as I mentioned before, has already been updated. This is a tool that's in GitHub. And it already supports OpenGL 4.6 and the extensions that made up OpenGL 4.6. I wanted to briefly mention the ASDO features that we added. It comes from 2 extensions. So there's 2 new draw calls, multi-draw arrays indirect count, multi-draw elements indirect count. And the new thing about these functions is that the draw count, actually comes from a buffer. not from a parameter that you pass in. The buffer is the parameter buffer that you bind ahead of time before you make the call. And the idea is that the GPU would generate its own draw count. One of the things you can use with this is the GPU can actually cull stuff and generate its own work. So this is another ASDO feature. In other words, reducing driver overhead, getting the GPU to do more. We finally added anisotropic texture filtering. We fixed an issue with cracks you often get with shadowing when they come down at very steep gradients. When the ratio gets really big, we can now clamp that ratio to stop the light leaks. A couple of other extensions. So a parallel shader compile, I mentioned it earlier. This is something that came out a couple of years ago, but now it's a KHR extension, which means OpenGL ES can enjoy that as well. It's a way for explicitly the driver to advertise that it's doing compiling of shaders across multiple threads, and the application can limit how many threads it uses up. This is something that Khronos didn't ratify, but just a demonstration of the ecosystem doing really well is that there's a whole bunch of new cross-process and cross-API interop extensions, and these are vital for OpenGL sharing with Vulkan. Or other things, or cross-process and stuff like that. This is useful for example, doing your rendering in Vulkan, then making the OpenGL do the VR HMD. So now that's supported, and it works really well with the Vulkan interop extensions. And then we've added a couple of Windows extensions for KHR no error, so you can tell the driver to not check errors anymore, maybe reduce some overhead. Quick ecosystem update. The glue, the extension wrangler that's popular and widely used, now supports OpenGL 4.6, all the entry points. There is a OpenGL 4.6 reference card. Actually, we're giving some away. We have limited supply, so if you really want one, you better make sure you grab it before they run out. And the other thing that is changing in the ecosystem is that Khronos, over the last couple of years, has heavily invested in their conformance test suite. Conformance is very important. It's very important that all the different vendors supply the same experience, the same interpretation of the specification. So we've been investing in more coverage. And so to go along with OpenGL 4.6, we're releasing a new CTS suite, which are coming out in a couple of months. And we've picked up a lot of tests that the OpenGL ES guys have been developing as well. And the other big news is that the whole conformance test suite is now open source. So anybody can contribute. You can see the source code. You can mess with it, file issues. So in conclusion, OpenGL 4.6 improves the baseline feature set of the core specification. And we will continue to evolve and serve the needs of its customers. That is my job, and I will continue to try and do that. And I want OpenGL to remain a viable choice in the 3D graphics API landscape. It's going to continue to support legacy applications. There's a lot of them out there. There's a lot of businesses that rely on it. And it's important that OpenGL continues to serve those customers. And it's a high-level API for better and worse. And it's a place for people to play and innovate stuff. So happy birthday. Happy 25th birthday, OpenGL. Now, before I end, I do actually have a trivia question. And we will give out, I will give out a T-shirt, whoever gets the answer right. Okay, so it's a fairly easy question, so I'm just going to try and spot whoever puts their hand up first or shouts out the answer first. And then you'll get a T-shirt. All right, the question is, in what year was OpenGL 4.3 released? Oh, actually, I should have said, no Khronos members are allowed to answer this question. OpenGL 4.3, what year? You can make, yeah? A no? Yes. All right. Yeah. And just because you've been a wonderful audience, I actually have a very, very, very special prize to give out. So I don't know if you've heard of this product. It's an NVIDIA GTX USB thumb drive. So, actually, These are actually kind of rare. If you're a fanboy of the GTX brand, you know how rare these are, and if you go onto eBay and see how well they're selling, you know how rare they are. So this is actually a really good price. Okay, so this question is a little bit more difficult. What was the name of the API that was the precursor to OpenGL? Don't forget, no Khronos members allowed to answer. Yes. No, that doesn't sound right. Yes. Who said RSGL?
Sorry for the accent.
Oh, is that what you said?
Yeah, French accent.
Okay.
Actually, it was GL. It only became RSGL to distinguish it from OpenGL. I used to work on
All right, that's it for me. Thank you so much. Oh, I got a few minutes of questions. All right, any questions? Yes. Yeah, sure. Yeah.
We have people following online on the live stream. That's why we are encouraging people to use the microphones.
Now that spirv is part of OpenGL Core, are we going to get binders texture extension?
Good question. We haven't started talking about it, but
because that would be really useful for doing things on NVIDIA, for example, that support binders texture.
Okay.
It's the right way to do OpenGL.
Okay.
But we can't use spirv now.
Mm-hmm. Okay, yeah, noted. Thank you. Any other questions? All right, Tobias, thank you.
Hi. Too close, sorry. So I'm here the OpenGL ES chair to talk to you a little bit out of OpenGL ES. I won't be going for quite as long, and I'm afraid I don't have any cool prizes to give away, but such is life, I suppose. So status of OpenGL ES, it's very prevalent these days. ES2 is basically everywhere. There's something like 1.5 billion devices out there, and they all support OpenGL ES2. 3.x ES versions of ES are now at about 6% market penetration. I've got that from the Android stats and from Unity's Hub statistics as well. 3.1, 3.2, kind of hard to read from those statistics, but it's there and it's increasing. There's not, again, any plan for a new core version at this point. As far as we can tell, the market need for it is being kind of displaced by Vulkan. That's not to say we're not paying attention. There's still extensions being developed by our members to try and fill any holes that need filling. But at this time, we've not found any need to standardize on anything and ratify anything. But as I said, we're currently still watching the market to see if there does develop a need for it. So we're not going anywhere yet. And whilst we're still here, we are focusing on quality of life stuff, trying to make OpenGL ES and the experience of coding to that API much better. One of the main things that I started doing last year was addressing the massive backlog of issues we accumulated over the years, over the last nearly 14 years now. And there was something like 300 to 400 issues that we hadn't addressed, and that's now gone way down. We're currently sitting at somewhere about 30 issues that aren't assigned to spec editors. And we're probably looking to, maybe before the end of the year, do some spec updates for ES to address a lot of those, because there's a lot of stuff that's just sat waiting for spec editors to write the language that we've proposed and actually put a spec out. Alongside this, we've done some other stuff. GL Slang now supports OpenGL ES 3.2 shaders, which has been a while coming, but is now there, so you can do verification of your GL ES shaders for ES 3.2. And then the other big thing really is our CTS effort, which I'll go into. So as Piers mentioned, the CTS is now open source. This is true for all three of our graphics APIs, ES, Vulkan, and GL. It's all a shared code base, in fact. And some of the sharing, as Piers pointed out, about them taking on some ES coverage, we've taken on a little bit of GL coverage as well, as we've now got a shared code base, so that helps. It was open sourced in January. It did take a while. We've been saying for a few years now that we'll be open sourcing it. We did finally do it. There is one small remaining part that is closed source. We're poised to remove the dependency fairly soon. I don't know the exact release date yet, but sometime hopefully before the end of the year that will be gone, and the whole thing will be out there. So there's been 3 releases so far. We're still very much on top of adding new stuff and getting features tested that weren't being tested in the past. We've secured funding for another year of development, and, well, actually less than that now, but it's addressing a lot of important holes of coverage. And again, the backlog of issues we've had with both CTS and the spec, and any spec changes that are needed changing, they're being done and addressed now. In terms of extensions, we've had a lot of EXTs added to the registry over the last year, and one KHR extension, which Piers mentioned. It's actually kind of annoying. I wanted to tell you about that at the last SIGGRAPH, because it was released about a week after SIGGRAPH last year. But, you know, such is how things go. But obviously some shared extensions here that also, you know, GL has. In fact, most of these, there's a few novel ones. There's a number of minor features and platform interactions, and again, there's the content sharing stuff that you've also got in GL. These are all for importing memory objects and synchronization from mostly Vulkan, but also from platforms as well. So that's all I've got to say on OpenGL ES. I assume I have a little bit of time for questions if anyone has any, but otherwise we'll go to Tom. Does anyone have anything to ask? Okay, thank you. Tom?
So we're clearly moving into an age of leaner, meaner, more efficient APIs because we're almost 10 minutes ahead of schedule. We may have to have the party early, or we can have lots of Q&A. In any case, hello, my name's Tom. I actually am Tom. So this format here is going to be a little different, sort of reflecting the youth and energy of Vulkan, I like to think. I'm just going to give a very shallow overview of kind of the breadth of things that are happening without much detail. And then we're going to have other members and friends of the working group come up and go, you know, so I'll give you the overview of what has happened in the past year, and then they'll go into deeper dives on some of the details. Hopefully everybody knows what Vulkan is, so I can kind of skip this mostly. You know, we started out with various technical goals, and you know what they are, and it was all generally in the service of efficiency and predictability, particularly for real-time graphics, but of course you can use it anywhere you care about those things. And that was explicit when we started the project. In the course of doing the work, we found ourselves sort of accidentally evolving also an equally strong feeling that there were things we needed to do about the way we engaged with the community. I should say we were all coming out of the OpenGL ES development process. We felt a need to try to be more community-facing, to say that this is a new API, you know, it's coming, it has no legacy, there is no reason for people to adopt it. The way that we can best help it succeed is to view it as a partnership between the traditional people who have pushed APIs, GPU vendors, et cetera, but also equally the developers, who were strongly represented, by the way, in the Vulkan committee, and platform people, because it takes all of those working, otherwise you don't have a successful ecosystem. The open source thing, it's not necessarily the drivers. Some of us have open source drivers, some of us don't, but it's really the whole ecosystem, the conformance test, the SDK, the loader, and in fact, the source, the specification source. So GL's 25 years old. That's really impressive. Vulkan is kind of at the other end. A year ago at SIGGRAPH 2016, Vulkan was 6 months, and it had the virtues but also some of the vices of the age. It was very clear that it had a lot of potential. It was certainly the center of a lot of attention and a lot of energy and anxiety, but it wasn't actually doing all that much. There were some awesome demos, and there was some drivers of reasonably good quality, although there were issues there certainly. But it was mostly a story about the future that we were telling at SIGGRAPH last year. Whereas now, well, it's still kind of a work in progress, but there's certainly been enormous improvement in the functionality of the whole ecosystem. There's you know, new capability. We've certainly learned a lot, and there have been some surprises, frankly, and some rather unexpected directions that the ecosystem and the API have taken. But generally very positive, and I'm extremely excited about it, and of course, as I think we all are. So to go into those in just a little bit of detail. So last year at SIGGRAPH, we had drivers of varying quality. Some were production, some are not. Now on the desktop, all of the big three developers have production drivers. If you update your driver from AMD or an NVIDIA, you will have, in addition to the latest GL and DX support they have, you will also have Vulkan. You even have drivers for things like this, my crummy corporate laptop. I will confess that I had to go to the Intel site. Lenovo doesn't yet have it in their drop. But yes, I can get a driver for the Intel embedded graphics in my APU. On platforms, Linux support is excellent. We have the official support in Android. That is, there's a loader there in Android 7. You can ask it, what Vulkan do you support? You might say, I don't. But at least you can ask the question and you can adapt to that. And of course, you can filter on the Play Store, can't you, Jesse? Of course. There's, of course, Steam and Steam VR, a flavor of Linux, but with a very distinct character, and there's Vulkan support in that and a lot of product shipping on it. In the Windows, we have excellent support on Windows 10, including this crummy corporate laptop. Windows 7 picture is a little dicier, but it's coming, and I think it's pretty solid with AMD and NVIDIA. I think maybe not with Intel. In the mobile space, a year ago we had the Samsung Galaxy S7. That was the only store you could buy in the only phone you could buy in a store that had Vulkan. There were some developer early releases for Android N, as it was called at the time. Now, with Android 7 out, there are tons of devices. Samsung, went from the Galaxy S7 to now dozens of tablets and phones. Huawei's got a large number. There are phones from Sony and Xiaomi and a number of Google products of different types, plus others. I know all this because there are also awesome community resources like vulkan.gpuinfo.org, where you can get a catalog of crowdsourced descriptions of all of the implementations that people have bothered to upload. One point I want to make in the mobile space is that it's not just a premium device story anymore. Samsung, at least, are deliberately aiming at mid-range devices as well as high-end, and that's critical to us to have a wide ecosystem with a lot of the ability to provide value to a lot of consumers. And I should say it's not all phones and tablets either. We've got special purpose devices and gaming entertainment focused devices like Switch and Shield. To the other end of the spectrum, moving from hardware to software, last year we had interesting demos and some early products, and there was I think Talos Principle was in full release, maybe it was still a beta, and of course there was Doom, which got a lot of attention. But it was still definitely experimental. This year it's much more production. Production Unity 5.6, Unreal Engine 4. I'm particularly excited that the Crow Team guys who do the Sirius engine, they were first to market with a beta game in the Talos Principle. They've since announced that they're doing all of their new products with Vulkan paths. So Sirius, Sam, up through the latest and greatest are adding Vulkan support. Support in the Oculus SDK for VR, as well as, of course, Steam VR. There's a beta of Mad Max, and as of last week, there's a beta support for Vulkan in the Crytek CryEngine, so that's pretty awesome. And there are rumors of varying degrees of credibility, pretty robust in the case of Quake Champions, a little more speculative for the others, but Ashes and Wolfenstein as well. So those are coming, but they're not here. And that, of course, is just the desktop. In mobile, there is tons of stuff happening. I'm not going to go into it in detail, but it's really awesome having the support in Android 7 provides a ready channel for people to push content to capable devices. you're all engineers, so you also want to see numbers. Pretty pictures aren't enough. These are the download stats for the LunarG SDK. Thank you, Karen. Where did Karen go? There she is. For the data, you know, it's a noisy signal, of course, but the bottom line is that the download rate has doubled since launch, so that's good. On GitHub, another of my favorite measures of developer interest. A year ago, there were about 400 odd projects that connected on GitHub that were Vulkan related in some fashion. That's tripled. I'm going to highlight just two. I just learned, they're not the best, but I just learned about them, so I'm really excited about them. NVIDIA R&D has a framework called Falcor that they use for rendering research. It's on GitHub, and it used to be DX12 only, but as of quite recently, it now also supports Vulkan. There's also an awesome new debugger. I think it's pronounced GAPID, but maybe it's GAPID. It's GAPID? Okay. Yeah, the Google guys are saying. Okay, so GAPID is a new debugger focused on Android, but it handles all of the Android graphics APIs, so GLES, GLES2, and Vulkan, and has a number of awesome features, but I'm behind schedule, so I'm not going to talk about them, but ask us later. The working group's been very busy. I'm going to skip most of this because other speakers are going to address it. I did want to highlight in the conformance area, we've nearly doubled the number of Vulkan test cases in the Vulkan conformance test. That includes all of the new KHR extensions because we don't release those unless there is a conformance test. But also a lot of new coverage to improve the behavior of 1.0 core implementations. Also, after 18 months of incredible agony, as I said, we keep the source code, the source text of the specification on GitHub, and we can now, according to the lawyers, take your pull requests. So if there's a typo, if there's a bug, and there certainly are bugs, or if there is just unclear language in the Vulkan specification, you could always raise an issue on GitHub, and we would get to it eventually. But now you can raise an issue and provide a fix, which probably means we'll get to it sooner. So we encourage you to do that. Without further delay, I'm going to turn it over. Jan-Harald is going to talk about some of the new extensions. Neil Trevett and Ralph Potter will talk about people who are building things on top of Vulkan or extending the reach of Vulkan in various ways. Nguyen from Google will give us the latest on the state of HLSL support in Vulkan. It's actually quite good. Karen will introduce some new features that have been added to the ecosystem recently. And for the grand finale, Rolando Caloca will give us the state of Vulkan support in UE4. Okay? Sorry. Jan-Harald, please come up. By the way, they're going to start bringing in food and drink maybe as soon as 5:30, but they're not going to let you have any. So don't run for the table as soon as they come in. Hang here, do the Q&A, and I promise at 5:45 we'll break.
All right. Hello, so I'm Jan-Harald. I work for ARM in the GPU team there. So as you've probably noticed, we don't have any new core API version for Vulkan today, but we are working on developing features that will eventually go into it. And so in the meantime, we're releasing features as soon as we're ready with them and they have conformance tests as extensions, so you can start using them earlier. And if you look in the Vulkan registry now, we have about 40 Khronos ratified extensions. We have a few experimental ones, and then there's a bunch of cross-vendor and vendor-specific extensions as well. And so more is not necessarily a goal, but it does show that there's a fairly healthy development of things going on. One note on the KHX ones, so that's something fairly new. We started doing around GDC this year, in that we're releasing experimental extensions. So they're not final. We reserve the right to just change them at any time. So they're there so you can start playing around with them and give us feedback, and then eventually we'll turn them into KHR extensions. So experiment, don't put it into production code because they will do bad things. So the first few, these are fairly old extensions. I'll cover these quickly. We had a maintenance 1 extension, which is basically things that didn't turn out quite right when we shipped 1.0. And so there's a bunch of minor fixes that were put into that. So I think the two key ones that I highlight is the better support for 2D array layers, so you can copy between 3D slices and 2D arrays, and also the ability to flip the viewport so that you can match the coordinate space in other APIs. We released the draw parameters, which gives you new built-in variables to using in relation to instancing and multi-draw. And then the final pack, or not pack, but a set of extensions are not terribly interesting in themselves, but there were a few structures in the API that we didn't make extendable in the first core release. And we've since realized that that makes it difficult to build extensions on top of them. So all these things are basically just extensions that let you build other extensions on top of them. And so one of the bigger things we've done in the past year is the memory sharing. So Vulkan 1.0, basically the only communication you had out of the API was you sent something to the swap chain. And then there was no real way to get anything into the API or all the way out of the API. And that works fine for like the basic gaming use cases, but for integrating it into systems, that's not really sufficient. So we have a set of extensions that do memory sharing, which lets you import memory objects and export memory objects from Vulkan. And this allows you to share things across devices, across process boundaries, and across APIs as well. And the way these are structured is that there is a sort of independent, platform-independent core, which is the basics of the API, and then there are platform-specific memory types that you can import. So file descriptors for Linux-like systems and Win32 handles for Windows-like systems. To go along with this, there's a dedicated allocation extension, which basically allows you to say, well, for this memory object and this resource, I will have a one-to-one mapping. And sometimes that allows certain optimizations to be done in the driver. And for some of the sharing use cases, the drivers will require that. So there's a query API which lets the implementation say, look, I need you to have a dedicated allocation for this. Yeah, so, and if you're sharing memory, you also need to synchronize access to that memory, fairly obviously. So there's a similar set of APIs that lets you import and export semaphores and fence objects. Yeah, I should also say these were also previously experimental extensions. So at GDC, we released them as KHX. They have now been upgraded and blessed, so they are final. And so Piers already mentioned this, but since they share these memory objects, they now allow you to import things between various APIs. And they're not necessarily only the Khronos APIs either. So since there are Win32 handles, as long as you can get one of those, you can import that into the various APIs. Another fairly big gap in the initial release of Vulkan was the multi-GPU support. So if you have a couple of GPUs in your desktop PC, you kind of want to use them both. And so that's now, these extensions, the device group extensions let you do that. So they give you explicit control over what runs on which GPU. And the basic mechanism they use to do that is that all of the API works the same, and then there's a device mask that gets inserted in various places in your command buffer, in your render passes, and in your queues, which let you specify, well, this goes to that GPU and that goes to that GPU. And so some of these features, like the memory sharing, is also important for the VR use cases. We also have a couple of things more directly related to that. So there's a multi-view extension, which is similar to the extensions we've previously had on OpenGL ES. But they basically let you record a draw call or a command buffer that can go to multiple views expressed as an array texture. So this saves the number of commands you need to do to draw through your multiple views. And this is specified as additions to the render path structure. So the render path now can have multiple views in it, and you can have a view mask, which lets you say, well, which of the views that a particular draw call goes to. The shared presentable image gives the display and the GPU access to the frame buffer at the same time. So basically, this is front buffer rendering, which you really, really need to cut down your latency. And the incremental percent is, well, not related to the VR use case, but related to composition, where you can provide regions that have changed, and so that you can pass those through to the compositor, and so that you can avoid recompositing things that haven't changed. Another couple of things we've done is to add a couple of extensions that change the way you update descriptor sets. So one thing that was given as feedback to Vulkan 1.0 is that often if you want to update large amounts of descriptors, you basically end up with the application setting up a whole bunch of these write descriptor set structures every time, and then you call the update descriptor set function. But if it's the same set of things that you update very often or every frame, then it may be possible to do things more efficiently if you just bake that information once. So the update template lets you do that by setting up all your offsets and number of descriptors and all that once. You store that template, and then you can pass that inside with your application-specific structure, and then the necessary copies happens as part of that. We also added something called push descriptors. So we had push constants in the original API. This is kind of similar. So it lets you update a small number of descriptors directly in line in the command buffer. And this basically gives you a more GL-like update model of descriptors. So it has some pros and cons. One of the pros is that it may make it easier to port existing contents. So if you have existing stuff that calls bind texture for every draw call, this may be an easier path. The final big bag of stuff is compute shader improvements. So we have two extensions for that. One is the 16-bit storage, which gives you 16-bit types in various interfaces and blocks, and then the variable pointers. So I'll skip this now because we have separate talks on these features and what they're used for. A couple of other minor ones. So the storage buffer storage class is also more of a convenience thing. So in spirv, we previously had a storage, a uniform storage buffer class, which was used both for like SSBOs and uniforms. But it turns out that hardware treats those fairly differently, and so it's useful to separate those classes so we can describe things more clearly in the specifications. And then finally, our latest extension, which got released earlier this week, which is relaxed block layout, which basically just lifts some restrictions on what offsets you can have in your buffers, and this improves our compatibility with the HLSL shading language. Finally, coming up, we're not quite done yet. So I did mention maintenance 1. There is also maintenance 2 because we didn't fix everything in maintenance 1. So a few things we expect to fix in that extension is to allow depth stencil images to to allow you to have one part of that be read-only when the other part is write-only and vice versa. So currently you have to have both of depth and stencil in the same state, and that has some issues, so we want to fix that. We'll add the ability to let you view compressed images as integers, so you can do the transcode kind of type stuff. We had another coordinate problem where it turns out we sort of accidentally flipped the origin of the tessellation domain, which we didn't quite mean to, so we'll fix that. Yes, and then let you query how we do point clipping. Subgroup operations, aiming for shader model 6-like functionality for that. And then a couple of additional features we need for the VR use cases. So we need protected memory, so you can stream protected content through. And we need color space conversions, so you can have video data coming in. I think that's my last one. Yes.
Okay, I'm going to spend a couple minutes talking about the Vulkan portability initiative. And the first question is, why do we need Vulkan portability initiative? Because Vulkan's already portable. It's been designed from the get-go to be implementable on pretty much any system. But Vulkan is not available on every system, not for non-technical reasons. Some DX12 systems, and certainly Apple systems that are now only shipping metal as part of their platform definition. So that creates obviously an issue for many developers, people developing games engines, native apps that need to run everywhere, and browsers, which are also, of course, a universal application needs to run everywhere. It's the #1 question I get asked about Vulkan is, when can we get Vulkan on Apple? So we figured we'd try and help this problem. And back at GDC, we went out there with a straw man saying, well, perhaps we should design like a hybrid API. We should munge these APIs together, find an API that can map effectively wherever you're running to the underlying APIs. And thanks to you guys, the community, we got some really wise feedback and several dope slaps saying, don't do that. Please don't create a 4th API, because that's going to make things even worse. So which, of course, is exactly correct. So we went back to the drawing board, and we came up with a plan B, which is not to create a new API, but to simply list the functions in Vulkan that won't map to the other APIs. Create a portability subset of Vulkan that native games and potentially, at some point, the next generation of WebGL can use. This would be a universally portable API. The last time we had a universally portable API was OpenGL ES 3.0. And then Apple didn't ship ES 3.1, and things began to be non-universal. So the idea is to create this subset that can be directly mapped to the underlying APIs, so we don't lead people off a software emulation cliff. This subset would be pretty much native performance. So that's the project we have ongoing. We're established as a subgroup of Vulkan. So we're not hijacking Vulkan. Everything we do gets agreed and reviewed by the main Vulkan working group. But right now we're doing the overlap analysis between the 3 APIs to see what that API surface of the intersection is. And the early results coming in, I'm sure it's not a surprise to most of you here, it's actually looking pretty good. The APIs are not diverging terribly. Overall, they're kind of converging. And already the overlap surface is like 85% or more. You lose some of the 3D parts around the edges. So you might lose some of the last degree of optimization opportunities. But of course, that's a choice. Some people, foregoing those edge parts of the API might be a good trade-off for the universal portability. So we want to provide people that choice. So we're going to end up with a set of deliverables. We're going to have a specification that defines what the intersection spec is that you can use. We want to create a Vulkan tools layer that you can plug in, and it will tell you, it'll warn you, if you're using features that are not available in a portable universal sense. And I was talking to one of the journalists this morning, and he suggested we call that the metal detector, which I thought was quite good. TM. We want to produce an open source library that will map your Vulkan calls to the underlying APIs, either Metal or DX. And we're fortunate we already have the spirv translator, which will take your Vulkan spirv and translate it back into source for either Metal, shading language, or HLSL to put through the native compiler chain on those platforms, because of course you need your shaders to be portable, not just the API calls. And a set of conformance tests, which is easy because we're not creating a new API. We don't have to recreate everything from scratch. We can just subset the existing conformance tests. So the overlap analysis is in progress. We have spirv cross. We might find some gaps, but spirv cross is already out there. And there are projects out there already too, looking at the API mappings. GFXRS is one that's been sponsored by some of the folks from Mozilla. And it already maps onto Metal and DX12. And so, there's that, and we might get other contributions too, but it's already out there. So come and help if this is interesting to you guys. And I sneaked in one other topic, but it leads into Ralph's presentation coming up, which is how is OpenCL going to try and help with Vulkan roadmap? Because OpenCL is at a kind of interesting milestone. We spent several years getting OpenCL C++ defined. So now OpenCL, latest version, is 2.2. We have C++ from top to bottom. You can use it in SYCL, single source. You can use it as a kernel language. So we kind of finished. We kind of finished what we've had in our heads for a while. What are we going to do next? There's been a lot of discussions. There's one kind of track. Actually, we've ended up with 3 kind of projects. One is the C++ track. There's a lot of people working using the C++ language for parallel programming. SYCL is the Khronos track. And we all kind of share a kind of good goal that we really call eventually, if standard ISO C++ were to enable heterogeneous parallel programming. There's a lot of work, a lot of discussion in the industry about that, and we hope that SYCL can help with that long-term goal. It probably is a long-term goal. We're probably talking a decade or so, but it's worthy, and we need to help. There's a realization suddenly that we've been too desktop focused. There's a bunch of embedded and DSP vendors who want to use OpenCL for things like vision and neural net inferencing as the hot topics of the day. And yet, OpenCL is sitting there mandating IEEE 32-bit floating point. We're disenfranchising a big potential OpenCL community, so we want to do a DSP profile of some description. We need to decide what that is. But the reason I'm talking that here in Vulkan is we want to help bring OpenCL class compute into Vulkan. So we have almost a decade. Next year is OpenCL's 10th birthday. A lot of experience in figuring out how to do heterogeneous compute. A lot of the sessions here at the show have been about the importance of better, more flexible, easier to use compute, and so we want to help. But this isn't, don't panic, this is not a takeover bid. Everything is going to be under the control of the Vulkan Working Group, but there's a lot of expertise that we hope can accelerate that process. So those two things, they kind of multiply, I think, in goodness, because if we can have Vulkan, at least a strong subset of Vulkan being universally portable, and over time we bring OpenCL class compute into Vulkan, we get a universally portable graphics and compute API, which is cool for many people. And what Ralph is going to be talking about next is a really interesting first step that just appeared a few weeks ago. Some of you might have spotted it in the press, that Google and Adobe and Codeplay have been working together on an experimental compiler to take OpenCL C and compile it to Vulkan spirv, so you can run it in the Vulkan runtime. And Adobe, turns out, they have 200,000 lines of code that they've let this project use as an experiment. And they've successfully compiled that much production code already. So it's kind of a proof of concept, I think, that this merging of OpenCL compute kind of capabilities with Vulkan is going to be a very interesting project. And Ralph is going to talk in a lot more detail about that. Thank you.
Hello, everyone. So I guess Neil's done my introduction for me. I'm Ralph. I work at Codeplay. I'm going to talk about porting OpenCL C to Vulkan. So this was an experimental piece of work that was a collaboration between Google, Codeplay, and Adobe. Adobe gave us 200,000 lines of real production code from real Adobe products, and we really wanted to know what's the gap between Vulkan compute and this real-world OpenCL C? What do you need to provide to get this stuff onto Vulkan? So we set out to build a compiler that would compile that code and to give us a sense of what things you need to do and what parts of OpenCL are maybe less used and maybe not immediately necessary. So there's a bunch of things you have to resolve, and it basically comes down to the differences between Vulkan spirv environment and OpenCL C's requirements, or alternatively, OpenCL C versus GLSL. So it's things like pointers and fixed size types, certain things to do with control flow and that sort of thing. Now, it turns out it's pretty, somewhere between hard and not possible to do this without some extensions and some modifications to Vulkan. So I'm also going to talk about a couple of Vulkan and spirv extensions that we used along the way. Now, I'm going to talk about OpenCL C, but you can also think of this as a proof of concept for other pointer-based languages. If one day you want to get C++ as a language generating spirv, this is one of, but not all of, the steps you need to do along the way to get there. So, first of all, why would you want to do this? Vulkan, it might not quite be everywhere, as Neil kind of discussed in the portability discussion, but it's on a lot of platforms. It's on more platforms, or at least it's on platforms where OpenCL doesn't exist. And so it provides a route on if you can get this thing to work. So first of all, there were a couple of extensions that are directly applicable to this. The first one is the 16-bit storage extension, which is pretty straightforward. Essentially, you get to use 16-bit types in shader interfaces, so in input and output interfaces, in storage buffers, in push constants. This has nice kind of bandwidth reduction potential. It also helps us deal with fixed size types in OpenCL C. So OpenCL C allows you to declare kind of a short integer, for example, and we need a way to do that. The extension only gives you load and store and conversion to and from 32-bit types. It's not giving you the full compute, but it will still be enough to do the bandwidth reduction, and you can promote to larger types to do the rest. The other thing we needed is the variable pointers instruction. This is not quite general purpose pointers everywhere. What this gives you is a per invocation pointer which can dynamically point into storage buffers and optionally into workgroup storage. So you can't get a pointer to a private variable, you can't get a pointer to a function variable. The Vulkan compiler still has a lot of latitude about what it does with those things, but for externally visible storage, it gives us pointers, and it gives us a way to dynamically manipulate them, do address computation, select between multiple buffers, and that sort of thing. So moving on to the compiler itself, it's a prototype OpenCL C 1.2 to Vulkan compiler. And by prototype, I mean it will blow up on you in certain circumstances. It's definitely experimental. It tracks the top or the top of tree of LLVM and Clang. It's not a fork. So you can just go to GitHub, pull the actual compiler, pull the latest releases of LLVM and Clang, at least as of 2 days ago when I last tried it. And it should all build fine against tip-of-tree, LLVM and Clang. And essentially what we're doing is some work to map OpenCL address spaces to spirv storage classes. We're translating OpenCL built-ins to the extended instruction set for Vulkan. And we're doing a bunch of work to map pointer arithmetic down to these variable pointers and to deal with the complexities of things like typecasting that you can do in OpenCL C, which is a little less friendly in spirv. So the basic flow is that you feed in an OpenCL C file, we feed it straight into essentially something close to the stock Clang front-end library. That generates what was the old version of spir prior to spirv, which is essentially LLVM IR. And then we have a bunch of internal LLVM module passes that massage that into a form that can be safely consumed by a Vulkan runtime. So we can emit a spirv file, and we can emit a second file that essentially tells you what the descriptor maps are that you need to correspond to the kernels. So on the left here, I have a sample OpenCL C kernel. It's pretty straightforward. The one thing of note is that we have a select between 2 pointers based on our global ID, so our invocation ID in spirv. And if we start to translate this into spirv, the first thing we're going to do is just translate our buffers, what are storage buffers in Vulkan. We get some pointer access changed to those. You could do that without the variable pointers instruction. That's just a uniform static address calculation. We map the get global ID built-in OpenCL C down to just a read from the global invocation variable, which is unfortunately somewhere off the top of the slide, but we can't get all of it on the slide. But this here is a dynamic select between 2 pointers. Without the variable pointers extension, we couldn't have implemented this particular line. Then here we're just doing a division based to do our kind of compaction here and getting another pointer chain to our destination and doing our final write. So it's pretty straightforward, but there are a few bits that we couldn't have done without the extension. Now, there are some limitations. There are some OpenCL built-ins that simply do not have Vulkan or HLSL equivalents today, so those are not supported. Similarly, there is support in OpenCL C for very wide vectors, which we don't have in Vulkan. And also, we've kind of taken the easy way out, and where OpenCL has very strict precision requirements for compute, we just went with the default precision that Vulkan spirv provides you. Pointer sizes, or pointers remain unsized as they are in spirv, so you can't do size of on a pointer. We don't have byte addressable types, but despite all of these limitations, out of the 200,000 lines of code that Adobe gave us, there were 30 lines that we had to modify in some way, and all of them, once they were modified, the modified code went straight through the compiler. So in reality, at least for Adobe's real-world code, we're pretty close. There are some things that are missing, but that's where we are right now. And on that, I just want to acknowledge Google and Adobe for their help on the project, and then I'll pass on to the next speaker.
Hi, my name is Hai. I'm from Google, and it's not lost on me that it's a Google person talking to you about HLSL. But Tom wants everybody to get excited about HLSL, so hopefully I can fulfill that. So here's an overview of the high-level items that we'll cover in this talk. It's very quick. First of all is how does HLSL work in Vulkan? And after that are the 3 compilers that currently exist for Vulkan. All right, so how does HLSL work in Vulkan? Well, by compiling to spirv. Pretty straightforward. Initially, Vulkan had pretty much all the necessary bits to support most of HLSL. Most of the required plumbing had a direct mapping of concepts from what was required in HLSL to Vulkan. Some of the other concepts that didn't quite fit in required a little bit of jiggering, but eventually it worked. There are some upcoming changes, or I guess one upcoming change to Vulkan to accommodate some of the HLSL things. As Jan-Harald mentioned, it's the extension for adding HLSL style unaligned buffer access. And essentially what it does is it adds the float 3 configuration within a 16-byte boundary. And obviously there's ongoing work to add more coverage of HSL in the Vulkan tools. And so the first up is GL-slang. GL-slang is in large effort by Khronos, Google, LunarG, and the community members out there. It has the distinction of being the first compiler to support HLSL and Vulkan. And the HL support is complete enough at this point for it to be used in real-world projects. Two notable examples of this is Dota 2 and Ashes of Singularity. So which shader models are supported? Currently, most of SM5 and some of SM5.1 is supported. And the specific features of these are largely driven by community ask. So if there's something that's missing, please go to the GL-slang repo and make a feature request. So let's take a look at the supported features. So all the shader stages work, and for the supported HSL features, the source can be compiled unmodified. There are some difficulties with using opaque data types, and there's ongoing development to get those resolved. The HLSL registers map to binding numbers, and normally they map to the 0th descriptor set, but you can override this by using the resource set binding flag at compile time, or you can just use spaces in HLSL. The location for I/O variables is based on declaration order, and this is the same as how FXE works. And you can use entry points other than main. So VS main, PS main, your compute shader. System value semantics are matched based on, or matched to their corresponding built-in type for Vulkan if they're supported. User-defined semantics are not currently supported. And this is always a mouthful. The CVV, SRV, UAV types are all supported. The notable thing about UAVs is that if they have a counter, then there are 2 binding slots consumed. The mapping of HSL resource types to Vulkan resource types can be a little bit tricky. I tried to summarize this as best as I could here. If you have any questions about this, please see me at the after party. Combined image samplers work, but it's probably not recommended. I tried this on an NVIDIA card earlier, and it seemed okay. It may be undefined behavior, but what somebody told me earlier. And of course, the spirv that's generated by GL-slang does work with the existing spirv tools. And just a little bit about working with GL-slang in production using HLSL. The resource types the resource descriptor types are not namespace the same way that they are in DirectX. So at times you will have to shift the resource binding offsets to get them to fit into your project, and you can do this at the command line. And if you don't want to do this and you're going to pull them out via reflections, then you can use the automap bindings flag. And next up we have Shader C. Shader C is a Google project, and it's the lead on the project is David Netto. And Shader C depends on GL-slang, so the HL support is roughly the same. There is a slight bit of lag because Shader C uses its own GL-slang repo as opposed to the one at Khronos. And Shader C can also optionally execute spirv-opt as part of the build process. When you're working with the flags in Shader C to change the binding offsets, they're slightly different, but they pretty much do the same thing. There are some different limits, default limits. An example of this is the max draw buffers. It's 8 in Shader C, but it's 32 in GL-slang. And lastly, which is why I'm up here, is if you haven't heard of BXC, it's Microsoft's open source HLSL compiler for Shader Model 6. And Google is contributing a backend to it that has adopted the moniker spirv-egg. If you're familiar with the history of Clang and GCC, then you know where the name comes from. DXC is based on LLVM and Clang 3.7. It only supports HLSL, and it targets only Shader Model 6 and higher. As I said, Google is contributing the spirv back into it. Essentially what it does is it takes the front-end code that is generated by the DXC compiler and it generates spirv as a result. It's an active project within Google, and this is a project that is being worked on with Microsoft, so all the changes are being mapped in actively. And a little bit of progress on this project is that all the math types, operators, flow control statements are operational. System variables and arbitrary semantics are working in Vertex Shader and Pixel Shader. The first initial test showed that pass-through Vertex and Pixel Shaders work. And the supported normal structs and array types of emitted debug names also work. And that's pretty much it. I think next up is Karen.
Sure. Questions afterwards? Okay. Hi, I'm Karen Ghavam from LunarG, CEO Engineering Director. So mine will be pretty short and fast. I just wanted to introduce a couple new additions that will be seen in upcoming Vulkan SDKs, and they're already available out on the GitHub. So I'm going to talk a little bit about the LunarG device simulation layer, and also some new spirv optimizations that we've been working on. And of course, if you have any questions or want to have any dialogues with the engineers who actually did this work and are 10 times smarter than me, but I'm smart enough to know to hire them, feel free to send email to info@LunarG, and I'm sure that we'll be able to get any questions answered that you may have. So, starting out with the LunarG device simulation layer. It's a layer that sits in between the ICD installable client driver and the application. And the purpose of this layer is to enable some application testing when you don't have all the hardware in your possession. And it does this by modifying capabilities that are returned from Vulkan queries. And the device configuration is actually defined by a JSON configuration file. And use cases might be, for example, you want to look at, fallback paths in your code in your application when lesser capabilities are present. Is my application really doing what I want to do? Or you may want to test for like unintentional assumptions you might have in your application, that when you remove some capabilities, suddenly some new validation errors will get triggered if your application isn't written to be able to accommodate that situation. Or you just want to constrain the resources that are available to your application and see how it will behave in that environment. So we felt like this would be a very useful tool to help application developers when they're testing and they can't buy all that hardware or have it all in their possession. They can begin to do some testing on this. I wanted to emphasize that this is a simulation and not an emulation. And sometimes the meaning between those is not, the difference is not really clear to each other. So let me talk a little bit more about what we mean. It's a simulation in that the results from queries are changed from a more capable device to simulating a less capable device. But it's not emulation in that once you remove a capability from that query, it's not going to enforce that perhaps that more capable hardware you actually have to be less capable. So if your application ignores the results from queries and goes ahead and tries to use the capability on the GPU that's there, we will not enforce it, okay? And it's not an emulation in that it doesn't add more capabilities. This is not like emulating a Vulkan device in entirety, okay? So think about it's taking away capabilities from more capable to less capable. So a JSON schema file has been created to validate configuration files that you use as input to this layer. And we have put the schema out at schema.khronos.org. We just finished that last week, working with them to get it out there. We have worked with Sasha Willems and his database, vulkan.gpuinfo.org, to make sure that all his configurations are compliant to this schema that has been defined as well. And he has actually done some modifications for us and also has added a button to download schema-compliant configurations for you. We're continuing to do more development on this layer. It's just the very first release, preliminary. We want to start looking into adding extension support, meaning add the existence extensions or remove the existence of extensions so an application can see how it will behave if an extension is or is not there, or modifying formats such as RGB formats, stencil planes, etc. We're looking at memory and queues. It gets a little bit more complicated there because it's not a matter of just removing some capabilities out of a larger set of capabilities. You have to figure out some mapping for types and families. So we would love it if anybody has some use cases or suggestions or input on, how they could see that might be useful for them during their application development. So it's available now. You can find it out in the LunarG Vulkan Tools repo. The developer was Mike Weibelin at LunarG. Please submit issues, questions, enhancements, whatever you have to Vulkan Tools. We will be putting the binary for this layer in our next SDK release that we're planning to do very shortly after SIGGRAPH. And you can also contact Mike Weibelin directly if you would like to have some dialogue with him. So that was the device simulation layer. Moving on, different topic, context switch here. We've also done some work working with David Nadeau a lot at Google and also Dan at Valve on doing some spirv optimization. So we all know that the size of spirv is a challenge for some people and something that people are interested in finding ways to bring the size down of their shaders. So we have done some work to do some optimizations focused on size. And so what you'll see on the left is a typical workflow of someone coming from HLSL or GLSL to spirv. Spirv-opt, in the middle, we have made some modifications in there to do these optimizations. And the optimizations include inlining or store load elimination or aggressive dead code elimination and common uniform elimination. And we worked very closely with we ran it through all the shaders for Dota 2. And we ran it through other shaders from some other ISVs that I'm not privy to really be able to mention here. But of course your mileage will vary, but what we did see is that we would get to less than 40% of the original size of spirv by using these optimizations. And then we did a comparison of how does it compare to DX bytecode if I'd taken HLSL and created DX bytecode. And so we're less than 40% larger than what we would get with DX bytecode. So some very positive size reduction results with these optimizations. So what's next? There's more work to do here, but we wanted to make sure this got out and we made it, people aware that these optimizations exist. We want more coverage. Yes, we have put thousands of shaders through it, but as you know, the more shaders, the more usage, the more robust and higher quality that these optimizations will get. We're going to work on inlining, no growth optimization, time improvements, and loop unrolling. And we're also going to do some exploration around constant folding and Ghavam sub-expression elimination. So please use it. Submit your issues. Copy greg.lunarg when you submit your issues to, so make sure that he sees them. If for some reason you're uncomfortable with submitting your issues publicly, that's okay too. You feel free to contact Greg at LunarG, and he would be willing to assist you as well. So I think that was it. Rolando is next.
Well, got a ton of time left now. So, my name is Rolando. I work at Epic. I've been working on Vulkan for a while. So, I'm going to talk about where Vulkan is right now on UE4. So, last time, a year ago, year and a half, the first SDK was released. We're all very happy about that. A couple of weeks later, we released ProStar, which was the demo shown on the Samsung S7 launch event. This was using the mobile renderer, which is our feature level ES 3.1 capability level. It looks nice. Then we had later that year Lineage 2 Revolution, which was using Unreal also. So what had we been doing the rest of the year? So this is where we're at today. This is an example of shooter game rendering on the shader model 5 render, which is the third and the full render. This is like the sample project that comes with the engine. This is the infiltrator demo running on Vulkan. It's Unreal Tournament. This is the editor running, so we have the full editor running. This is some Paragon assets from our MOBA game. And then finally, our biggest showcase of graphics prowess, Tappy Chicken. So, as I mentioned, the shader model 5 is the default renderer right now for Vulkan. Before that, what we had at the end of last year was the shader model 4 renderer, which includes basically the D3D10 style techniques, which without compute. So if you go to the latest GitHub today, you can just add -Vulkan, and that's what you'll get. So, but there are some bugs, just don't tell anybody. So part of the changes to get Vulkan running and the other rest of modern APIs was to change the API of the RHI itself, which is our layer to talk to each individual API. So it's more compliant with them, and basically it's more explicit, like all the modern APIs. For example, we now require explicit transitions for resources. And pipeline states are now first-class citizen of the API. Before we just had loose state, set depth stencil, set call mode, etc. So now we have this little struct that has the information for the PSO. It's a little verbose, but it's just keeping in line with Vulkan. So we've been focused on stability mostly and visual parity. I'll talk about performance in a little bit. We'd fixed a bunch of stuff for Vulkan. We rewrote a bunch of the code. I guess half of the RHI was rewritten. Fixed a lot of graphics issues. And then, with every SDK, we get a lot of validation, new validation warning messages and errors. So we've been fixing a lot of those. And this is for 4.17, which is right now available, the preview. But the latest, we missed the cutoff date to integrate more fixes. But the latest main GitHub has even more fixes today. So we're going to push like next week, I think. You'll have even a more stable version of the RHI. And our goal is to have it as a default RHI in Linux. So sorry, GL 4.3, but now we're moving to Vulkan. So what is our to-do list? What we're working on as soon as I get back home. The main thing we're going to have to work on the CPU side is the scripter sets. We need to improve the layouts. Right now we're just having a set per shader stage. So as you can see there, I have uniform buffers and a few textures there. But this works fine in general, but then we get materials from Paragon or from Unreal Tournament, and the list gets a little crazy. And they do use all 28 textures. So we run into some issues where we have, the binding, we have index 32 in the binding, and somewhere places we just have an Uint32 mask. So obviously, a lot of code to fix around. But fixing this and rerunning this in a nicer way will also improve our runtime updates, which is part of the CPU problems right now. On the GPU side, and also we want to add parallel RHI threads. So the renderer right now enqueues commands to the RHI, which runs in another thread, and that's what generates the Vulkan commands. So what we want to do is obviously go wide as possible, more than 3 boxes, but I could just fill 3 here. And this will also, one of the problems with this is having the layout on barrier tracking, which I'll talk about in a little bit. So why it's a problem. But this is where we want to go to get the most performance, basically beat the X11 with it. So on the GPU side, we're still missing some features, like we don't have distance field AO or distance field shadows yet. These are known problems that we just have to fix, just run out of time before coming to SIGGRAPH. And what we want to do also is do a deep dive with Radeon GPU Profiler and RenderDoc, basically finding all the redundant transitions and barriers, finding redundant and empty render passes, and use more the async queues and the multiple queues in general. So I mentioned render passes. So one thing we're going to do after we fix all those problems is having render passes as a first-class citizen of the RHI. So there will be the code basically defining a render pass object. Then we would insert the commands, and you will not be allowed to insert other commands that could be risky or you can't do in the render pass. That'll simplify the coding model a lot. And that way we could do less tracking, and it will help with transitions. In this little example I put, all those yellow spots are potential transitions that people are doing right now. They're just transitioning the depth buffer from readable to writable to general to readable to writable all over the place. By having a begin and render pass, we could reduce that a lot. It'll help with tracking, so the tracking doesn't have to be as extensive. We don't have to be looking into maps or arrays all the time to see what's the current state of the current resource. Another big thing we're doing, and this is a huge change, is we're going to have support for offline, or cooked, as we call it, pipeline shader objects, pipeline state objects. So the problem with Unreal right now is that it allows you to do a lot of stuff. For example, we have the classical, oh, I want to dynamically spawn a point light with atmospheric fog for a skeletal mesh that has morph target in a blueprint. So that means we had to compile all the shaders before that could have any combination of those modes. So the little table at the bottom is basically a matrix of things you need to know to create a PSO. Right now, we just compile shaders separately, and at runtime, we match the vertex inputs, the run target formats, and then the rest of the material state. So one of the things we're going to do is reduce the number of vertex formats by doing the dynamics vertex fetch. That way, we remove one of the lines of one of the columns of the matrix. We're going to also find out the run target formats, and we already know the material state. So with this, we can just pre-create the PSOs at cook time. And then the rest of the PSOs that we don't know the information of, we think it's going to be, we think we'll know like 90–95% of all the used PSOs at runtime. So only things like the call state, we're hoping that with the pipeline cache, it won't cause huge stalls creating the PSO. And the PSOs are created asynchronously also. So yes, and removing the vertex formats, making it all dynamic, will also help us reduce the total number of shaders compiled. So you can see the little matrix at the bottom. It's all, couldn't remove the lines, but it's just one column. This will also help with titches, I mentioned, because we'll just create the PSOs when we load the material. And we still, before we get there, we still have a mode right now where you can just play through the game and then you can save the current pipeline cache. So the next time you start the editor, it will just load it. A longer term, we'll add support for tessellation and multi-GPU support. I added this bonus slide for debugging tips. I figured to get something useful, at least, of this part of the talk. So the usual is use validation layers. You know, they're your friends and your worst enemies, so just get close to them. Use RenderDoc to find problems, all the graphics problems you have. The Radiant Graphics Profiler is awesome. That allows us to not have to build the code to test the GPU feature on a console, so we could see the timeline of what the GPU is actually doing and how much time it's taking. Like we just do it directly on the PC. And then the last two things. So these debug modes to submit command lists, I highly encourage you to add them. Basically, so you can submit after every render pass, after every dispatch, and after every bleed and copy. That way, that's part one, right? So then, if you do that, sometimes when you're doing the dump with of the API itself, it just gets so much text that it's hard to read. So you can pause it there, basically, and then flush the log, and then you can see all the commands. But the main reason is to add another mode where you can do wait for idle after every submit. And this is great for tracking GPU hangs, which we've had a lot. So that way you can find out exactly which draw call, or which is the last area of the render where it died. And finally, just keep the shader source at runtime if possible. In our case, we go from HLSL to GLSL, then GLSL to spirv. So we're saving the GLSL as part of the runtime. That allows us to cross-reference a particular material. And thanks to these guys, and stay for the party.
Thank you, Rolando. Well, so amazingly, we're ahead of schedule, very unexpected. We kind of, because we were so expecting to be late, that's why we kind of didn't stop for Q&A before. But we can do Q&A now. I think, so there's audiovisual guys filming. I don't know if we stand there, will you be able to see us? Or? Okay, so speakers, if you could come on up. Even Piers can come up if he wants to, if you've got more GL questions. And we have a mic there, and can we have a runner with a mic, I wonder? It's just, that, again, because we're streaming, it's really nice if you ask your questions online. Okay, Emily's going to...
Line up right here.
Okay, so yeah, if people would come up front and fire away.
Hello, so I have a question for Vulkan and Unreal. What's the performance? Have you done any performance measurements on the games that have been shipped on Vulkan?
None of the games that have been shipped myself. So we have a mobile team. Those guys deal with that part. I help them a little bit. I've been focused myself mostly on desktop. Because of all the things I mentioned, we're on parity with E3D11. Sometimes a little faster, sometimes a little lower, maybe plus minus 10%. But we expect to be 50 or 60% faster once we go wide on the CPU.
And how does it look on the VR front?
I don't know a lot. There's a VR team. We're working on a bunch of different APIs. I don't know how much I can say, to be honest.
I appreciate it. Thanks.
Someone else, surely.
So I was curious, with SIGGRAPH 2018, what's some of the goals you guys are optimistically hoping to see Vulkan at next year?
That's a tough question because we've all got our own lists. I mean, I think, of course, everything's enabled by critical mass, right? So there has to be a big enough footprint of Vulkan-capable platforms for people to say, okay, that's going to be my default. That's where I want to get. Do we get there in 2018? I think we will in some markets. I think things are going quite well on the desktop where we have updatable drivers. Mobile adoption curve is slow, and people are going to have to ship OpenGL ES versions of their games, and that conditions a lot of your design work. That it's like a drag. So I guess my goal is adoption. Who else has got something? Maybe it doesn't work. All right.
Just say on the OpenGL ES front, one of the things I would say is that if you're thinking, oh, maybe I'll target ES 3.2, at this point, Vulkan is basically tracking at the same rate as ES 3.2 is. So it's it feels like it's more of a first choice, at least if that's what you want to do. I mean, there's still people who are going to want to code to a lower level than an engine or whatever who will be attacking ES 3.2, but I think a lot of developers now will be targeting Vulkan at that rate. Obviously, there's still ES3 that's got more adoption, but that transition is happening. Oh, and then the actual front, I think the main thing I want to see is more ecosystem stuff. There's been a lot of great tools being developed, like the CL spirv compiler and things like that, and I'm hoping we get a lot more of that.
Well, from a LunarG and an ecosystem perspective, the last year and a half, we've been very heavily focused on validation layers. The progress that's been made in the last year has been phenomenal in actual coverage, but it's not done. And actually, will probably never be done, but I would say from a year from now, I would like us to have the valid usage checks that really matter completely done. So that we can really be focusing on development of more tools to aid developers in their application development efforts. That would be my view.
Okay, I guess we're short on vision here. Go ahead.
My question is mostly, while watching the videos that Khronos published over last year, depending about Vulkan mostly, most of the users of Vulkan, different engines, mobile, desktop, they claim to have naive implementations and yet still able to match OpenGL either for performance or battery life, stuff like that. And I would like to basically validate my understanding. although they are naive implementations, it gives me hope in the sense that I will able to port my OpenGL application and achieve OpenGL driver level performance. Is that expected? For example, even Unreal, they are. Is my understanding they don't use multi-threading yet, which is probably Vulkan's most important feature, but still achieve DirectX 11 or close to DirectX 11 performances. Is this understanding correct?
Yes, correct. It's only one of me, unfortunately, and I get pulled to other stuff. But I mean, we're working on it.
So I mean, I would say in general, of course, if you use multi-threading, if you can, that's good. It's relatively tricky to add to your engine if you don't design it in from scratch. But you kind of get the low overhead for free once you have gotten rid of all the validation warnings and gotten the code actually rendering correctly. The only gotcha, I guess, is that I certainly have heard cases of people saying, well, I took my highly optimized GL or DX11 application and I read the manual and the spec and I carefully ported it and I put in all weights and dependencies everywhere I should to make it safe, and it runs correctly at half the speed of DX11. And yeah, you can have that experience. It happens because the GL or DX11 driver was optimizing your code for you and moving things around under the hood, and the Vulkan driver doesn't do that. So it is possible to go to Vulkan and have a slowdown. The guys are naturally humble and maybe undersell a little the work they did in getting those early applications working.
So my question is again to Rolando. You mentioned a little bit about layer transitions. So I was wondering if you had any chance to profile the different image layouts or those kind of things that you have. Like, is there a difference between having it in like the general layout versus having it in like read-only, for instance?
Yeah, we've heard a lot that we should not use general ever, if possible.
Okay.
I think that's like a known thing. But we haven't measured because we didn't have the tools yet. But now, last week, with that gradient thing, I think we'll get better numbers and see exactly where things are hurting, like how much really you gain or not. But I haven't measured it, so.
Okay, thank you.
Hi, so thanks to all the speakers for your talks. One of the questions when you were presenting about the portability initiative, this group working on getting Vulkan on all these different platforms. So you obviously presented all the work that's going on that has a technical solution to some of these problems, and there's a couple different efforts going on. Right. Is that group also going to look at some of the political and communication problems, or is it going to be purely technical? Is there someone that's trying to open a line of communication with the metal devs and their managers to say, hey, let's get 100% matching?
We always want to build bridges. It's kind of like a core value. We never make enemies. We want to open up communication channels. And the portability API is whether or not the web community uses it in the end, there's still value in the native side. There is some uncertainty around what happens with the next generation of WebGL right now, but we want to. What we're going to do is just keep sticking to our knitting and make sure that that Vulkan portability solution is done as quickly as we can, as well as we can, and then hopefully it'll add value to the larger ecosystem. And in the meantime, yeah, we want to build communication. We don't want it to descend into weird political battles because no one wins. And we just want a good solution for the industry.
Thank you.
Anyone else? We don't have the food yet, so we need more questions.
We can have the food at any time.
I mean, there was the question about 2018. Well, so big visions, my big vision is that we're continuing to grow and expand the footprint and becoming a preferred target. But lots of short-term technical objectives, like Rolando talked about the importance of being able to inspect time course of events and benchmark and analyze your performance better. We have some ideas for trying to do that at an implementation independent level. It's a hard problem because different hardware has different ability to support that kind of inspection. But that's certainly something we're very, very interested in doing, and any ideas that people have, we want to hear.
Yeah, just to one of your comments, Tom, where you said, oh, no one has any vision. I think it's probably worth pointing out that we do have some, well, quite a lot of it for where we're going with Vulkan, but we're not ready to talk about most of it yet. So don't worry. I promise you it's in safe hands.
How many people have changed their code to be all running on Vulkan, I guess? Just to show hands.
That's what I call a growth opportunity.
How many people are planning to do Vulkan ports?
Yay, thank you.
Actually, I had a question. I'm allowed to ask a question? Okay, good. I had a question for Hai. You talked about 3 different tools for generating spirv from HLSL. Is there any guidance about which one people should use?
The thing is that there's not like, I'm going to answer as honestly as possible. There's not any bias in this because John Kay, the lead contributor for GL Slang, also works for Google. So currently, from my perspective, and I think most people would probably agree, GL Slang is the most direct path from HLSL to spirv. And you can optionally run spirv-opt as a post-process on it and to get some basic transformations. I don't think it does any full optimizations yet, but it's the most solid path. And the reason why I'd recommend it is John Kay and the community that backs GL Slang is incredibly vicious in their attempt to solve this problem. There are times when I've posted an issue at 2 a.m. in the morning, go to sleep, I wake up at about 7, and John Kay's already fixed it. So GL Slang is definitely the way to go currently.
Another observation I'd make is that currently GL Slang is used for most of our conformance test shader generations. So the kind of code that it generates is better tested in implementations than other. However, we have an explicit plan to bring in as many other sources as we can. So we are going to be running conformance tests on other generated code, both from DXC and ShaderC, but also if you are one of the people out there who has an engine where you generate spirv straight from a block diagram or something like that, we definitely want your input because we need to exercise as many spirv executables as we can find.
Came up with a question after that last answer. Is there any plan for a spirv validator? Like you could take a chunk of what's supposed to be spirv code and see if it's actually valid spirv?
That is something we have had on the roadmap for a long time, recognizing that people wanted to generate it and needed a way to check that it's syntactically correct. I don't know the state of that project. I don't.
It's pretty good, right? We have one.
We do have one. Okay.
It's never going to be perfect, but it's workable.
So it's up on GitHub under the Khronos group.
Yeah, it's in the spirv tools. It exists. I know we use it internally. I don't know the state of it, and David would know for sure. But it's certainly better than not having it at this point.
So, you know, we invited you all to ask questions. We've certainly got questions for you too. We are interested. You can tell us now, or you can tell us privately during the party, but we're very interested to know. Okay, so not that many people have built systems yet, judging by the show of hands, but maybe some of you are just shy. We need to know your points of pain. We need to know things that you just have trouble understanding, because, you know, let's face it, it's not the most transparent and simple of APIs. It reflects the complexity of the hardware that it exposes. But, you know, what are your priorities for us? Those are useful things to know.
Just had a question of, if you had a new programmer, how would you actually teach them to do either graphics or compute now?
Sorry, to do?
Graphics and compute. Oh. What would be your favorite way of teaching them now?
Help. WebGL. No, I mean, Vulkan is explicitly, you know, I like to say Vulkan's not a graphics API in any stretch. It has a couple of data types that are graphics specific and a couple of operators that are graphics specific, but it's basically an API for controlling modern GPUs. And its structure mirrors them much more than it mirrors the structure of graphics computations.
Oops, that was louder than I thought it was, sorry. You know, at least for most of the university courses I've seen, you know, you tend to find that there's some graphics abstraction there in the first place, right? No one teaches OpenGL from day one. They teach some abstraction there that either they've invented themselves or they've got from the internet or whatever. And you wouldn't jump straight to Vulkan in any case. You wouldn't jump straight to OpenGL. So I think the progression is similar there. But, you know, maybe there's a position here where you could go from an abstraction to Vulkan. But I don't think you would go straight to Vulkan for any of this.
I talked about the massive activity on GitHub, and there's quite a lot of stuff out there that are superb tutorials, and you definitely want to take your new programmers, you probably want to filter the tutorials because, you know, the syndrome. But for example, the LunarG SDK has a whole bunch of good stuff. What else do we particularly like? Sasha Willem's stuff is awesome. Oh, okay.
I have one more comment.
Yes.
A couple months ago, you know, we have pretty large access to people who use the SDK from downloading, and so we had done a survey around the ecosystem, validation layers, loader, and what other tools, and are you porting to Vulkan or not? I have a lot of data, but I have to say that, you know, there was open places where you could do open, you know, open-ended and, you know, comments or whatnot. And one of the questions we were asking about, you know, what is your biggest inhibitors around being productive in Vulkan? And I mean, I had hundreds of comments literally about Vulkan is hard, or I don't have enough time, or what's my best way to learn this? And the thing that I have to emphasize is that Vulkan, it's not a graphics API, it's a GPU API, and it's very powerful. But it's not the place you start if you're new to doing graphics programming. It's not your first place to start out, so.
So I've just been informed that they're actually waiting until we stop talking to bring the rest of the food in.
I smell it.
So we have to get out of the room.
30 seconds.
Okay, yes.
Nick Whiting. So do you want to know the status of VR on Vulkan?
So on mobile, we still have a little bit of work to do, but with 4.17, which is coming out next week now, I think we got it up and running with Linux and Steam VR, so people can kind of give it a shot and see how the performance goes and whatnot. We haven't taxed it a whole lot internally, but it should be a good starting point if anybody actually wants to check it out as kind of an early access thing.
Awesome. Thank you all very much. So do come back and grab us and grab some food after they bring it in. Do we actually have to get out of the room? Okay, they're going to take the chairs out, so we need to go out there for a while. Thank you all very much.
Let's put the mic there.
Yeah. Yeah.
Whenever I asked the question, I also heard from my left here on the chip WebGL.
Right. For teaching graphics, WebGL is probably, I think that's what a lot of universities are doing now. It's either that or use an engine.
Yeah.
The trouble is they hide